Welcome to the deep dive. If you've been relying on MongoDB for your standard web application needs, you know it's flexible and fast, but you're likely using, well, only the top 10% of its capability.
hmm
Today, we are discarding that simple layer. We are embarking on a mission to understand MongoDB at the L6 and L7 engineering scale, the level where you need to deeply internalize not just how to query data, but how the system manages consistency, scale, and survival when deployed globally, and subjected to unavoidable network stress.
That's exactly right. We are drilling down past the data layer and really into the core of distributed systems engineering.
Okay.
Our sources today, they're rooted in comprehensive architectural guides, the kind designed for those high-level interviews, and that means we are unpacking the deep theory.
The really foundational stuff.
Yes, the mathematical guarantees underpinning its operation, the nuances of the Wired Tiger engine's internal guarantees, and the consensus algorithms that keep petabytes of data from fracturing.
Okay, let's unpack this. Our focus is sharp. We're providing the direct shortcuts to critical architectural knowledge. We're zeroing in on the hidden costs and the crucial trade-offs.
What?
The latency costs you absorb versus the durability guarantees you receive that fundamentally underpin MongoDB's behavior when the cluster is placed under massive, sustained stress.
And our journey, it really has to start with the immutable laws of distributed computing.
Yeah.
That framework that defines what guarantees the system can mathematically promise you, the engineer.
Let's begin then with the foundational concept for any large-scale system, the CAP theorem. I think many of our listeners can probably recite the three letters, CAP.
Sure.
But for a true deep dive, we need to formalize these definitions and really understand their practical implications for MongoDB.
Absolutely. The CAP theorem, defined by your accruer, it basically forces a choice. Three properties are consistency, C, availability, A, and partition tolerance, P. Consistency means that after any update, every subsequent read operation across the entire system returns the result of the most recent write. And that's a formal definition, requiring atomic consistency, a serial order of operations.
Got it. Then there is availability.
Right. Availability guarantees that every request receives a response within a reasonable time. The system must never block, essentially, even if nodes fail or are unreachable.
And critically, partition tolerance, P.
And P. This is the guarantee that the system continues to operate correctly despite arbitrary message loss or delays caused by network partitions, often called net splits.
Right.
And look, in any system of significant scale, a network partition isn't some theoretical failure case. It's really an operational certainty. It'll happen.
And this certainty forces MongoDB to make a defining choice. So for our listeners, what is MongoDB's fundamental position on the CAP spectrum, and why is that choice so decisive?
MongoDB is fundamentally a CP system. It prioritizes consistency and partition tolerance.
But, many modern NoSQL databases, they seem to prioritize availability first. For a system like MongoDB, which is often praised for its flexibility, why is sacrificing availability the sort of immutable choice during a network partition?
It really comes down to preventing catastrophic data divergence, what engineers call the split brain scenario.
Oh, okay.
If you allow both sides of a partition network to keep accepting writes, prioritizing A, when the network eventually heals, you suddenly have two conflicting versions of history.
A nightmare to reconcile.
Exactly. A near impossible task that sacrifices consistency. So MongoDB prioritizes C and P to prevent this. When a network partition occurs, the system takes the decisive and immediate action to halt writes on the minority partition.
Halts them completely.
Yes.
Yeah.
This prevents the smaller partition from creating conflicting data and maintains that consistency invariant across the surviving majority.
So the availability trade-off is really clear then. The minority partition effectively becomes read-only, maybe even unresponsive for writes during that event. And this safety measure is enforced mathematically through the concept of quorum.
Correct. The safety mechanism is that mathematical guarantee that enforces the consensus rule. Quorum equals the floor of n divided by 2 plus 1 node. So quorum n2 plus 1.
Right.
You must have a strict majority of nodes to elect a primary and therefore to accept writes.
Okay, let's break down the math for scale.
Yeah, let's look at the mathematics of scale. In a simple 3-node replica set, you need 2 nodes. That's a 66.7% majority. If you scale up to, say, a 7-node set, you require 4 nodes. That's a 57.1% majority.
Okay, so the implication here is that the larger the cluster, the statistically easier it is to maintain quorum percentage-wise, maybe? But the absolute number of failures you can tolerate is fixed and, well, relatively low.
That's it exactly.
If you drop below that N2 year plus 1 threshold, the primary steps down and the whole set becomes unavailable for writes.
That's precisely the operational cost. The system prioritizes correctness over uptime in that specific failure scenario. However, and this is critical, this is the strong default. The crucial L6, L7 insight here is that MongoDB isn't totally rigid, it's actually tunable.
Ah, okay. So how does an engineer configure MongoDB to sort of lean towards AP-like behavior, and what's the exact cost, the risk of making that choice?
You can definitely maximize availability and throughput. You'd use a write concern of W1, meaning the write is acknowledged only on the primary, and you combine that with local reads from secondaries using read preference secondary.
So you're basically telling the system speed over safety.
Pretty much. You're saying I value speed over immediate durability or global consistency, but the cost is significantly increased risk.
How so?
Well, if the primary crashes before that write is replicated, the write is just lost, gone.
Ouch.
And if you read from a secondary that hasn't received the write yet, boom, you experience a stale read. So look, this decision might be appropriate for high volume, maybe ephemeral data like session logs.
But never for financial transactions.
Absolutely never for financial transactions or anything requiring strong guarantees. Hashtag B ACD properties in a distributed context.
Okay, moving from that global system guarantee, CAP, to the more local operational guarantee. Let's explore how MongoDB applies the classic ACD properties: atomicity, consistency, isolation, and durability, especially in a system that might span multiple physical servers. Let's start with atomicity.
Right, atomicity. The all-or-nothing guarantee. It operates at two critical levels in MongoDB. The first is the classic single-document atomicity.
This is the historical guarantee, right? The one that defines the core document model.
Yes, exactly. And it's non-negotiable, guaranteed by the WiredTiger storage engine. Any modification to a single document, even one that involves updating multiple embedded fields or arrays, it happens entirely or not at all. No observer will ever see a half-updated document, period.
But the significant leap came later, MongoDB 4.0, introducing multi-document atomicity via transactions. This must be exponentially harder to guarantee across, say, multiple shards.
Oh, it is. Much harder. Guaranteeing atomicity across different documents, especially across different shards, requires coordinating commits very carefully.
How do they pull that off?
MongoDB achieves this primarily by leveraging snapshot isolation, we'll talk more about that, and persistent undo logs within WiredTiger.
Undo logs?
Yeah. So if a transaction, let's say it's updating 3 documents across 2 shards, fails on the 3rd step, the system uses the snapshot mechanism and those undo logs to roll back every participating document to its precise state before the transaction even began.
Ensuring integrity for things like double entry accounting.
Exactly, where multiple documents absolutely must change simultaneously or not at all.
Okay, next up, consistency. How does MongoDB ensure the database transitions from one valid state to another, especially in a distributed setup?
Consistency has, well, internal and external components. Internally, the database enforces rules like unique index constraints and schema validation, if you're using it.
Yeah.
And thanks to atomicity, it prevents those partial writes within a document.
Right.
Externally, though, the application has to define what valid means. But the database's role is to ensure that when a write is committed, especially with something like majority write concern, it is durable and transforms the state predictably.
So a unique index check failing is basically the database enforcing consistency.
Precisely. It's preventing the creation of an invalid state at the database level.
Isolation. This is usually the trickiest property in distributed systems, right?
Yeah.
Dealing with concurrency, preventing concurrent transactions from messing with each other. How is that managed in MongoDB's MVCC framework?
Yeah, isolation is tough. It's handled primarily by providing each transaction with a consistent view of the data, mainly through snapshot isolation.
Okay, explain that.
When transaction A begins, it essentially freezes its view of the database at that moment in time. Any changes made by some other transaction B are completely invisible to transaction A until B successfully commits.
So it prevents things like dirty reads.
Exactly. It's highly effective at preventing dirty reads reading uncommitted data and also phantom reads, which is seeing new documents suddenly appear mid-transaction.
You also mentioned session causality earlier. What specific guarantees does that provide the client that maybe standard snapshot isolation doesn't cover?
Session causality is really crucial for the application developer's sanity, you could say.
Yeah, okay.
It guarantees that within a single client session, the sequence of operations respects causality. You get monotonic reads, reads never go backward in time, monotonic writes Writes are processed in the order you submitted them, and most importantly, the read your writes guarantee.
Ah, that's key.
It is. If you write data within your session, you are guaranteed to read that data back immediately on subsequent reads within that same session, regardless of replication lag happening elsewhere in the cluster.
However, isolation between different sessions requires careful selection of the read concern. Let's quickly detail those 4 critical settings an L6 engineer absolutely must master.
Right. Starting with the baseline. Local. It's the fastest. Reads directly from the current node's persisting copy, or maybe even its cache.
But the trade-off.
The trade-off is it allows dirty reads. You might read data that's uncommitted and could potentially be rolled back later, violating strict isolation. Available similar, mostly optimized for sharded clusters, but carries similar risks.
Okay, then we step up the safety ladder.
Next is majority. This is really the standard for reliable operations. This read concern guarantees that the data you read has been committed and, crucially, journaled by the majority of the replica set members.
So that gives you the strong read your rights guarantee across the cluster.
Yes, exactly. And prevents reading data that might get rolled back on a failover.
And finally, the highest bar, linearizable. What's the technical mechanism here? How does MongoDB achieve that real-time ordering without resorting to heavy global locking?
Right. Linearizable reads offer the strongest possible guarantee. They ensure operations appear to execute in a strict, real-time global order. The mechanism is essentially a 2-step process. The read first executes as a majority rate. Then, the system performs a kind of coordination check against the majority to ensure no concurrent writes that have already achieved a majority commit are invisible to the current read operation.
So it synchronizes without explicit locks.
Exactly. This synchronization process guarantees that real-time ordering and prevents any weird time travel anomalies. But, and it's a big but, it introduces significant latency overhead because of that required cluster coordination, often tens of milliseconds extra.
Which brings us nicely to durability. The D in ACID, the promise that committed data survives hardware failure. And this is directly tied to the right concern settings, isn't it?
Directly tied. Durability is essentially measured by how quickly and how widely the write is committed to non-volatile storage, like disk. With the common default W1, the data is committed only to the primary's journal.
What's the risk there?
The risk window is small, but it's definitely real. If the primary crashes and the oplog entry for that write hasn't been replicated and applied to a secondary yet, that data loss is possible. It's recoverable once the primary comes back or via oplog replay after failover, but it's a risk.
And the strongest guarantee, that often involves 2 components, right? Right, concern majority and journaling.
Yes. The strongest and often the necessary choice for high compliance applications is W majority J true. That J true means journaling enabled.
And why is that the gold standard?
Because it guarantees the write has been persisted to the journal files, the durable files of the majority of the nodes in the replica set. This level of guarantee ensures survival even if a minority of nodes experience simultaneous disk failures or crashes.
Can you quickly outline the path data takes for durability?
Sure. Data is first written to the in-memory cache in WireTiger. Then it's persisted to the write-ahead journal. That's the critical step for immediate durability. And finally, asynchronously, it gets written to the main data files during checkpoints. That journal is the only thing protecting the data between those checkpoints. Hashtag to hashtag C. Logical clocks theory. Lamport and Vector.
Okay, we've established physical clocks drift, making them pretty useless for ordering events accurately across a distributed system. We need logical tools to define causality. Let's delve deeper into Lamport clock theory.
Right. Lamport clocks provide a necessary, though, as we'll see, incomplete foundation for ordering events. It's essentially a scalar counter maintained by each process.
How does it work?
The rule is quite simple, elegant even. Local events just increment the counter by 1. When a process sends a message, it includes its current timestamp, let's call it $2. When another process receives a message with timestamp $2, the receiving process updates its own clocks using the formula. $2 match ICT plus PWAM. It takes the maximum of its current clock and the received timestamp, then increments.
Okay, and this gives us the property of happened before. If event A happened before event B, AB, then the Lamport clock value of A must be strictly less than B. So LCA, LCB.
Correct. That implication holds. But, and this is the single most important limitation about Lamport clocks, often misunderstood, the converse is not true.
Ah, okay. Explain that.
If LCA is less than LCD, you cannot definitively infer that A caused B. They could have been concurrent. Imagine a simple scenario. 2 concurrent writes. $W and $2W happen simultaneously on two different nodes.
Right.
Due to maybe network routing quirks, $W might simply arrive at some observer node first, giving it a lower Lamport timestamp, LCLCA $20 free. But they were concurrent. Neither cost the other. The system only tracks the potential for causality, not the definitive relationship.
So if you need definitive, precise causality tracking, knowing for sure if things were concurrent, you need the improved version. Vector clock theory.
Exactly. Vector clocks solve that precision problem. They abandon the simple scalar counter. Instead, each process maintains a vector, an array, with one entry for every other process in the system.
How does that work in practice?
When an event occurs locally, the process increments only its own index in the vector. When sending a message, it transmits its entire current vector.
And the benefit, as you mentioned, is perfect capture of causality.
Precisely. You compare two vectors, say $VD and $VD. If they are not comparable, meaning $V is sometimes greater and sometimes less than $VD2 across different dimensions or indices in the vector, then you have mathematical proof that the two events represented by those vectors were definitively concurrent. We write that as VD2. It's the gold standard for proving concurrency.
Okay, if vector clocks are so powerful for proving concurrency, why doesn't MongoDB, or frankly most large-scale distributed systems, actually implement them? What's the catch?
The scalability issue is a hard stop. It's the overhead. The overhead is, in other words, the number of processes in the system.
It's so linear with the number of nodes.
Exactly. Imagine a cluster with, say, 50 shards, each a 3-node replica set, plus 3 config servers. That's potentially over 150 processes. Every single message, every replication event would need to carry a vector of 150 plus integers.
Wow, yeah.
The storage cost, the bandwidth cost, the CPU cost of maintaining and transmitting these large vectors constantly across a globally sharded system. It's just prohibitive for high-throughput operational database like MongoDB.
Which brings us then to MongoDB's pragmatic choice for managing transaction ordering and consistency.
Right. MongoDB uses a more scalable approach. It uses Lamport clocks, essentially, or concepts derived from them, like uptime, for ensuring monotonic progress and basic causality across the cluster. This is combined with version numbers specifically for its multi-version concurrency control MVCC system within WiredTiger.
So it's a hybrid approach?
You could say that. It gives them sufficient causality tracking for replication and multi-document transactions without incurring that massive vector clock penalty. It's a practical engineering compromise.
Okay, let's shift now from abstract clocks and theory to the concrete architecture of the data itself. Starting with how data is actually encoded and stored on the wire and on disk. Hashtag ABMB eBSONing and the 16 MB limit.
Right. MongoDB relies heavily on BSON. That's binary encoded serialized object notation for both its wire protocol, how data moves between client and server, and its storage format on disk. It's a necessary departure from just using plain JSON.
Why is plain JSON insufficient, for a high-performance database? What specific advantages does binary encoding like BSON provide, especially at scale?
Well, the binary nature of BSON offers 3 really critical engineering advantages over text-based JSON. First, size efficiency.
Okay.
Numeric types, especially things like 64-bit integers or floating point numbers, are represented in their native binary format. This is way more compact than encoding them as decimal character strings like you have to do in JSON. This saves space both on disk and, maybe more crucially, during network transmission. Less data to send.
Makes sense. And the other 2 advantages?
Second is type safety. JSON is inherently a bit ambiguous about numerical types, right? Is 1.0 an integer or a float? BSON explicitly includes a type indicator, usually a single byte, preceding the value, which immediately tells the parser if the following value is an integer, a double, a timestamp, a binary blob, whatever. This removes interpretation ambiguity.
Okay, type safety, got it. And the third?
And finally, faster parsing. BSON documents contain fixed-size headers that specify the length and sometimes the offset of subsequent fields. This allows the database engine, WiredTiger, to perform random access to specific fields within a document much more quickly, without having to parse the entire document sequentially from start to finish. This is absolutely vital for efficient reads and especially for targeted updates.
Right, jumping straight to the field you need. But even with the efficiency gained from BSON, there are still limits, which leads us to the famous, or maybe infamous, 16 MB document limit. For a flexible document database, that sounds pretty restrictive. What are the deep engineering reasons behind this seemingly arbitrary ceiling?
Yeah, it catches people out, but the limit is far from arbitrary.
Yeah.
It's actually deeply rooted in maintaining internal architectural integrity and performance. One major factor is simply memory pressure.
How so?
Documents have to be loaded into memory for indexing, for querying, for updates. If documents were allowed to be unbounded, say gigabytes in size, a single large document operation could potentially saturate the system's RAM very quickly, impacting all other operations.
Okay, memory pressure. What else?
The second, and perhaps the most critical factor, ties back to atomicity and MVCC, which we'll discuss more. WireTiger has to maintain multiple versions of a document for concurrency control these version chains. If documents were incredibly large, say many gigabytes, the history store required to maintain atomicity during writes would become entirely unmanageable. It would explode in size and lead to instability.
And I assume network efficiency plays a role too, right? Sending huge documents around.
Yes, absolutely. Very large documents inflate index entries, which hurts index performance. And they obviously complicate network transmission. They might exceed manageable TCP packet sizes, increasing the probability of transport layer issues like fragmentation and retries. The 16 MB limit ensures that, generally speaking, a document is a manageable unit within the cache and across the network.
So if an engineer does need to store large assets like high-resolution images or video files that easily exceed 16 million, what's the standard design pattern they are forced to use?
They must use GridFS. It's important to understand GridFS isn't some special storage engine. It's more like a specification or a convention built on top of regular MongoDB collections.
How does it work?
It chunks the large asset, the image or video, into smaller BSON-compliant documents. Typically, these chunks are around 255 kbps each. These chunks are then stored in a dedicated chunks collection, and metadata about the file, like file name, size, chunk order, is stored in a separate files collection. This ensures the system maintains atomicity per chunk and manages memory effectively, while still allowing the storage of arbitrarily large files.
Let's talk about the primary key in MongoDB. Very often, it's the objected. Can you break down its structure and explain why it's so well-tailored for a distributed high-scale system?
Sure. The objected is a clever 12-byte identifier specifically designed to be globally unique without requiring coordination between clients or servers. That's the magic.
How is it composed?
It's composed of three main parts, packed into those 12 bytes. The first 4 bytes are a Unix timestamp, simply representing the seconds since the epoch when the ID was generated.
Okay, time-based.
Yes. This is followed by 5 bytes that were originally a machine identifier and process ID, but are now often just a random value for better distribution and security. Finally, there's a 3-byte monotonically increasing counter, which is initialized usually to a random value per process or driver instance, and then increments for each ID generated within that second by that process.
The key advantage, you said, is its point of generation.
Exactly. It's designed to be generated typically at the client side by the application driver, like pmongo, mongoose, etc. This is highly efficient because it completely eliminates the database round trip that would otherwise be required just to fetch a unique ID before you could even perform the insertion.
Right. Saves a whole network hop.
And it provides guaranteed global uniqueness across all your clients and application servers, which is crucial in a sharded environment where multiple app servers might be writing concurrently.
And because of that timestamp prefix, it offers a utility that a purely random UUE, for instance, would not.
Precisely. Because the most significant bytes represent time, object IDs are inherently sortable and queryable by time. When indexed and the UTIC field is always indexed by default, its structure makes it highly efficient for B+tree indexing, especially for queries that need to retrieve data chronologically or filter based on insertion time. Show me all orders from the last hour. The time prefix helps a B-tree print search paths very effectively. #tag_tag_c, WireTiger storage engine, and MVCC.
All right, time to enter the heart of MongoDB's concurrency management. The WireTiger storage engine and its fundamental reliance on multi-version concurrency control, or MVCC. What specific concurrency problem does MVCC solve so effectively for a high-write system?
MVCC fundamentally solves the performance bottleneck of traditional locking mechanisms, like two-phase locking.
How so?
If you use traditional locking, a writer transaction would typically have to acquire exclusive locks, which would then block all readers, and potentially other writers, until the commit was complete. In a high concurrency environment, that just leads to severe throughput degradation. Queues form, latency spikes.
Okay.
MVCC flips the model entirely. Writers don't block readers, and readers don't block writers. Instead, it cleverly provides every reading transaction with a consistent snapshot of the data as it existed at a particular point in time, even while concurrent writes might be actively modifying the underlying data.
How does this work under the hood? Can you describe the version chain mechanics?
Sure. When a document is modified in WiredTiger, the engine does not overwrite the existing data in place immediately. Instead, it creates a new version of the document containing the changes. It then links this new version back to the previous version, forming a linked list or a version chain.
Where are these old versions kept?
These older versions are stored in a dedicated area, often referred to conceptually as the history store. Every version in this chain is tagged with metadata, including the timestamp or transaction ID of the transaction that created it. This chain of historical states is what allows the system to provide isolation.
So if a transaction, let's call it transaction T, comes along and needs to read a document that has multiple versions in this chain, how does the system decide which version T is allowed to see? This is the snapshot visibility function, right?
Exactly. The visibility function is the core logic. When a transaction dollar starts, it is assigned a consistent snapshot timestamp. Let's call it T-edgers. The rule is quite simple. T-edgers can only see versions V dollars, whose creation timestamp $2 is strictly less than $2's own snapshot timestamp $2.
So anything created after the snapshot was taken is invisible.
Correct. Any version created after its snapshot is invisible to $2. This ensures that T operates on a temporally consistent data set, protecting it from dirty reads, seeing uncommitted changes, or non-repeatable reads, seeing data change mid-transaction.
But this version chain requires the system to hold on to old versions, potentially for a while, until they are no longer needed by any active transaction. This brings us back to a potential operational hazard you hinted at, the history store eviction problem and maybe something called hazard pointers.
Yes, this is a massive potential issue at scale, a real L6, L7 operational concern. The history store, which holds all those old document versions, must eventually be cleaned up or garbage collected to reclaim space.
Makes sense.
The critical point is that old versions cannot be deleted if any active transaction is still holding a snapshot timestamp that might require visibility of those old versions. The system uses internal mechanisms, sometimes conceptually referred to as hazard pointers or snapshot holders, to track which versions are still potentially visible to any open transaction running anywhere in the system.
So let's play out a worst-case scenario. A client application starts a transaction, maybe opens a huge cursor to scan a large collection, and then pauses processing. Perhaps the client code has a bug or someone attached a debugger and it just sits there for, say, an hour. What happens inside WiredTiger?
That is the definition of a potential operational catastrophe. That single long-running transaction holds on to its historical snapshot timestamp. This prevents the garbage collection process in the history store from cleaning up any document versions created before TLs but deleted or modified after TLs.
So the history store just grows and grows.
It rapidly swells, potentially consuming gigabytes, even terabytes, of memory and disk space if the right volume on the cluster is high. This leads to severe cache thrashing because the active working set of current data gets pushed out of the main cache to make room for this ballooning history. The system has to constantly read old versions from disk, severely degrading performance for all other users of the database. L6 engineers absolutely must monitor the age and number of active snapshots constantly to prevent this. #TAG checkpoint algorithm deep dive.
Okay, we know the journal protects us between operations for durability, but the checkpoint algorithm is what ensures the large data files on disk themselves are structurally consistent and recoverable after a crash. Can you walk us through the steps of a full checkpoint process in WiredTiger?
Sure. A checkpoint is essentially the process of synchronizing the current in-memory state of the database with the on-disk data files in a consistent manner. Typically involves 4 main steps.
Step 1.
1. Consistent snapshot. WiredTiger first takes a consistent snapshot of the current database state in memory. This effectively freezes the logical time for the purpose of the checkpoint.
Okay.
2. Write dirty pages. Then, all the data pages in the cache that have been modified since the last checkpoint, these are called dirty pages, are flushed or written to the actual data files on disk. This I/O operation is optimized to be as sequential as possible to maximize disk throughput.
Makes sense. Step 3.
3. Update metadata. Once all the dirty data pages are safely written to disk, the storage engine atomically updates crucial metadata files. These metadata files essentially point to this new, consistent set of data files as the latest valid state of the database. This atomic update is the moment the checkpoint is considered successful and durable.
And finally,
discard old snapshot. After the metadata update confirms the new checkpoint is durable, the system can then flag the data files and associated metadata from the previous checkpoint as obsolete. These old files can then be eventually deleted or reused by the storage engine.
what are the timing implications of this process? How often does it happen?
Checkpoints occur automatically in MongoDB. By default, it's typically every 60 seconds. Or it can be triggered sooner if a specific threshold of dirty data accumulates in memory, usually around 2 gigabytes by default.
So there's a trade-off in frequency.
Absolutely. While the checkpoint process is designed to be relatively low impact, more frequent checkpoints do place a somewhat heavier, more constant burden on disk I/O. Conversely, less frequent checkpoints mean that if the server crashes, the recovery process will take longer because more operations from the journal log will need to be replayed to bring the database up to date from the last checkpoint.
This really highlights the essential journal versus checkpoint trade-off. How should an engineer think about their distinct roles in ensuring overall durability?
They work together synergistically. The journal is the write-ahead log, WAL. It guarantees durability between checkpoints. It's the primary mechanism for immediate crash recovery. If the system fails, say, 5 seconds after the last successful checkpoint, only those 5 seconds worth of operations recorded in the journal need to be replayed to recover.
And the checkpoint.
The checkpoint ensures that the main on-disk data files themselves are structurally consistent and represent a fully recoverable state up to the point in time of the checkpoint. It makes recovery faster by providing a solid baseline. You absolutely need both working correctly to guarantee high durability and reasonably fast recovery times.
Okay, when we start talking about guaranteeing data integrity across multiple nodes in a replica set, we inevitably talk about consensus algorithms. MongoDB, like many modern distributed systems, relies heavily on these principles, specifically borrowing concepts from the Raft consensus algorithm. ##a Raft consensus algorithm principle.
That's right. The main reason is Raft's relative simplicity and understandability.
Paxos is known for being complex, right?
Yeah, notoriously complex. Mathematically proven, yes, but incredibly difficult to implement correctly and reason about. It's sometimes jokingly called the Turing machine of distributed systems, powerful but arcane. Raft was explicitly designed with understandability as a primary goal, making it easier to implement, audit, and integrate reliably.
So MongoDB uses a Raft-inspired protocol. It's not pure Raft, but it integrates core principles. Let's look at those, starting with the concept of the term and voting theory.
Yes, the term is absolutely fundamental. You can think of it as the unit of time or an epoch number in Raft. It's a continually increasing integer. Every time a new election for a leader, or primary in MongoDB terms, is held, the term number increments.
What does that achieve?
This establishes the critical term invariant. There can be at most one active primary leader within any single term number. This immediately and elegantly solves the potential split-brain problem during elections. Nodes in older terms simply cannot win elections or accept rights.
And the voting mechanism enforces this term invariant.
Exactly. Quorum-based voting is key. When a node wants to become primary, it increments the term and starts an election. Followers can only vote for one candidate within a given term. Crucially, a candidate node must receive votes from the majority of the replica set members, remember our N2+1 quorum, to win the election and become the primary.
How does this prevent split brain?
This majority requirement ensures that only a node that has the support of the majority can become primary. And because a node only votes once per term, it's mathematically impossible for two different nodes to simultaneously receive majority support within the same term. It also ensures the elected primary has the most up-to-date log, or oplog in MongoDB. #tag_b oplog replication mathematics.
The engine driving replication between the primary and secondaries is the oplog, the operation log. Can you describe its structure and function? How does it act as the distributed source of truth for the replica set?
The oplog is essentially a special, fixed-size, capped collection that resides within the local database on every member of the replica set, primary and secondaries.
Capped collection, meaning old entries get overwritten.
Precisely. It records all the state-changing operations, inserts, updates, deletes, in BSON format. Each entry is annotated with an optime, which is MongoDB's way of combining a timestamp and a counter for strict ordering within that timestamp. Secondaries continuously tail or pull operations from the primary's oplog asynchronously and then apply those same operations idempotently to their own datasets, striving to keep up with the primary state.
At L6 scale, operating large clusters, we absolutely must discuss the most dreaded operational failure related to this, the oplog overflow problem. Can you explain the risk here and the severe operational impact of this scenario?
Oh yes, this is a common operational nightmare, especially in environments with highly variable traffic spikes or maybe intermittent network lag between nodes, perhaps in different data centers. Because the oplog is capped, fixed size, Old entries are eventually overwritten to make space for new ones.
So what happens if a secondary falls behind?
If a secondary node, maybe it's a delayed replica used for backups, or just a node that had network issues, falls too far behind the primary. Let's say it lags by 10 hours, but the primary's oplog, due to high write volume, only retains the last 8 hours of operations.
Uh-oh.
I was right. The lagging secondary eventually tries to fetch the next oplog entry it needs, say from 9 hours ago, but discovers it's gone. It's been overwritten on the primary. It has a missing link in the replication chain.
What's the consequence for that secondary?
The consequence is severe. The secondary cannot simply catch up incrementally anymore. The chain is broken. It is forced to perform a complete initial sync, often just called a resync.
Meaning it copies the entire data set again.
Yes. It has to wipe its local data and copy the entire current data set from another healthy member, usually the primary or other up-to-date secondary. For a multi-terabyte shard, this process can saturate network bandwidth and disk I/O on both the source and destination nodes for potentially 12, 24, even 48 hours. During this time, that secondary node is effectively offline, reducing the overall read capacity and fault tolerance of the cluster. L6 monitoring requires constant vigilance, checking the configured oplog window size against the measured replication lag for all secondaries.
And for sharded clusters, this complexity multiplies significantly, doesn't it?
It absolutely does. A common mistake is only monitoring the replication lag on the primary replica set, or maybe just one shard. In a sharded environment, you have multiple independent replica sets. Each shard is its own replica set and maintains its own separate oplog with its own size and window, and the config servers. They are also a dedicated replica set with their own oplog.
So monitoring has to be granular.
It's extremely granular. An oplog overflow might be happening on one particularly hot shard due to high write volume there, but you'd completely miss it if you were only checking the oplog window on the config servers or a less busy shard. You need shard-specific monitoring for oplog size, window, and lag. ###C. Read concern theory, formal definitions.
Okay, we've established the system defaults to CP, consistency and partition tolerance. Let's formalize the spectrum of consistency available to you, the developer, via the read concern setting. We can move from the fastest, maybe riskiest option to the safest, slowest one.
Exactly. The choice of read concern directly dictates the guarantee you get regarding the visibility of data, and it comes with an associated latency penalty. The stronger the guarantee, generally the higher the latency.
So the fastest option available is local.
Right. Local read concern means the read executes immediately on whatever node it happens to hit. Could be the primary, could be a secondary, depending on your read preference. The latency is minimal because there's no coordination.
What's the cost?
The cost is low isolation. You risk reading data that might be in the node's cache or even journal, but has not yet been committed by the majority of the replica set. This means dirty reads are possible. You might read data that gets rolled back moments later due to a primary failover.
Okay. Next up, the safety ladder is majority.
Majority. This is really the sweet spot for most operational safety needs. It guarantees that the read operation only returns data that has been acknowledged and journaled by a majority of the replica set members.
And this provides that crucial read your rights consistency pattern across the cluster.
Yes, it does. And critically, it prevents you from reading data that might be rolled back after a primary election or failover because you know the majority have already made it durable.
Then we have linearizable. This is the highest level of isolation, the strongest guarantee, often only necessary for specific control plane operations or configuration reads, right?
That's generally true. Linearizable provides the strongest formal consistency guarantee available. It ensures that operations appear to execute in a strict, sequential, real-time order, as if they happen one after another on a single machine, synchronizing with all concurrent writes globally across the cluster.
How does it achieve that without global locks?
As we touched on earlier, it typically involves performing a majority read first, and then doing an additional coordination step, essentially checking with the majority again to verify that its view of the data, its snapshot, is completely synchronized with the absolute latest successful majority write that has occurred anywhere in the cluster. It ensures the visibility function is globally consistent at that instant.
But that coordination adds latency significantly. This coordination inherently adds latency compared to a simple majority read, often by tens of milliseconds or more, depending on network conditions. This makes it typically unsuitable for high-throughput, low-latency application queries, but sometimes necessary for reading critical metadata or configuration where absolute real-time consistency is paramount. #tag city. Right concern theory safety analysis.
Okay, if read concern dictates visibility, write concern dictates durability and safety. Let's analyze the safety implications and the risk profile of the most basic option, often the default in some drivers.
Write concern W1.
Right. W1 simply means the primary acknowledges the write back to the client only after it has successfully written the operation to its own in-memory cache and potentially its journal file.
So what's the failure risk we need to analyze here?
The operational analysis must account for the failure risk window. If the primary server crashes instantly, say, a power loss or kernel panic, within milliseconds of acknowledging the write, but before that uplog entry has been successfully replicated and applied by any secondary node, then that acknowledged write is vulnerable.
It's lost.
It is technically lost from the durable state of the cluster. It might exist in the crashed primary's journal if it recovers, but until then, or until a failover occurs and the new primary takes over, without that write, the data is effectively gone. The client might need to resubmit it. This small but non-zero risk of data loss makes W1 generally unacceptable for transactional data or anything you can't afford to lose.
How does explicitly adding the journal guarantee using Jader change this safety profile?
Adding Jader to the write concern is an explicit instruction for enhanced persistence on the node, specified by the W parameter. It dictates that the acknowledgement must wait until the write operation has been physically written to the persistent journal files on disk on the specified nodes, or node if W11.
So W1 JTrue is safer than just W1.
Marginally safer against just a process crash on the primary, yes, because it ensures the primary's journal has it.
Yeah.
But the gold standard for durability across failures is combining journaling with majority acknowledgement.
Which is W majority JTrue.
Exactly. If you use W majority JTrue, you are guaranteeing that the write has not only been acknowledged by the majority of nodes, but has also survived immediate memory loss by being secured in the durable journal files on that majority of nodes. This is the difference between surviving a simple process crash versus surviving sudden hardware failure or simultaneous crashes of a minority of nodes.
So for the L6 engineer designing a new application, this really forces a crucial selection decision tree based on the application's needs.
Absolutely. It's fundamentally a cost-benefit analysis, a trade-off.
Yeah.
If you are building a system for, say, streaming non-critical sensor data or logging analytics events where losing a few seconds of data might be tolerable, then maybe maximizing throughput with the W1 is the right engineering answer for that specific use case.
But for critical systems...
But if you are building an identity verification service, or a financial ledger, or a critical inventory management system, where losing even a single transaction is extremely costly or violates regulations, then you must accept the added latency inherent in using W1 majority, JTrue. You might even need the synchronization costs of linearizable reads for certain configuration data lookups. You are consciously trading potentially milliseconds of latency for mathematical safety and durability guarantees.
Okay, eventually a single replica set hits limits. Scaling past the capacity of a single server requires sharding, which is MongoDB's mechanism for horizontal data partitioning. But sharding immediately introduces the complexity of managing how data is distributed, keeping it balanced.
Right. The balancer is a critical background process, typically running on the primary config server replica set member. Its sole task is to ensure a reasonably even distribution of data chunks across all the available shards in the cluster.
What's a chunk again?
A chunk is simply a contiguous range of data based on the shard key values. The balancer tries to keep roughly the same number of chunks on each shard. If the distribution isn't balanced, the entire benefit of horizontal scaling is negated. You often end up with one or more hot shards taking all the load while others sit idle.
How does the balancer decide when the system is sufficiently out of equilibrium to act? Can you describe the imbalance calculation?
The balancer uses a dynamic threshold based on the number of chunks. It periodically checks, usually every 30 seconds or so, and compares the number of chunks on the most loaded shard, the one with the most chunks, against the number on the least loaded shard.
And if the difference is too big?
If that difference exceeds a certain calculated limit, which is typically small, like 2 for small collections, but scales up logarithmically based on the total number of chunks in the collection, then a balancing round is triggered. The system decides it needs to move a chunk.
Okay, so it decides to move a chunk. The actual chunk migration process itself is a complex, multi-stage protocol designed hopefully to happen without user-visible downtime. How does that non-downtime donor-receiver protocol work?
It's quite clever. The migration protocol involves 3 key actors: the config server, which orchestrates and manages the metadata, the donor shard, the shard giving up the chunk, and the receiver shard, the shard taking the chunk.
What's a flow?
The donor shard first starts copying the actual chunk data over the network to the receiver shard in the background. While this is happening, writes for that chunk are still going to the donor. Once the bulk copy is complete, there's a very brief, critical section.
The lock phase.
Exactly. The donor momentarily prevents all writes to that specific chunk range. It then quickly updates the metadata on the config servers to point future requests for that chunk range to the receiver shard. Finally, it releases its lock, and the receiver takes over serving requests for that chunk. The donor then cleans up the old chunk data later.
And what's the real-world operational impact of that brief lock phase during the critical section?
This is where you can see performance hiccups during balancing. That brief lock phase, while typically short, maybe 10 to 50 milliseconds, can introduce temporary latency spikes for any writes or strongly consistent reads hitting that specific chunk range at that exact moment.
So if the balancer is very active.
Right. If the balancer is running aggressively, perhaps migrating hundreds of chunks because the cluster was very imbalanced, the cumulative effect of many of these small lock-induced spikes can potentially saturate disk I/O or cause noticeable application performance degradation. L6 monitoring often involves watching balancer activity and sometimes using settings like balancer throttle to limit the I/O load during peak hours.
Okay, a primary headache for operators of large, mature clusters is often the emergence of jumbo chunks. Can you define them and explain what they signal about the cluster's health or design?
Jumbo chunks are chunks that either technically exceed the maximum configured chunk size, which defaults to 256 millib these days, up from 64 millib historically, or perhaps more commonly, they are chunks that are marked as jumbo by the system, because the balancer finds it impossible to split them further due to the nature of the shard key distribution within that chunk.
What does that signal?
They almost always signal a fundamental flaw in the chosen shard key, or perhaps in the application's data access pattern. The balancer wants to split chunks to keep them small and movable, so if it can't, something is wrong.
What are the typical root causes of these unsplittable jumbo chunks?
By far, the most common cause is the use of monotonic shard keys. Think of using a simple auto-incrementing integer ID, or maybe even just a timestamp as your shard key. Since all new writes are sequential, monotonically increasing, they all land on the same chunk, on the same shard, the max key chunk. That chunk grows uncontrollably, way past the 256 millib split threshold. The balancer can't split it because there are no logical points within the key range inside that chunk to make a cut. All the keys are clustered at the very top end.
Any other causes?
Another common cause is using low cardinality keys. For example, sharding your user collection based on a country field where maybe 90% of your users are in just one country. That country's chunk will become massive and potentially unsplittable if the secondary key doesn't offer enough variation.
So how does an engineer resolve a situation where they have a critical table plagued by jumbo chunks causing hot shards?
Well, pre-MongoDB 5.0, the resolution was often manual and quite painful. It might involve using low-level commands like just.splitadd to try and manually define a split point if possible, but more often it could require a full cluster rebuild with a better shard key, involving significant downtime and effort.
But things are better now.
Much better. In modern MongoDB 5.0 and later, the solution is significantly safer and less disruptive. Online resharding. This feature allows engineers to effectively change the shard key for an existing collection in the background without incurring application downtime. You can use the reshard collection command to transition, for example, from a flawed monotonic key to a much more distributed hashed key, thereby resolving the jumbo chunk and hot shard pressure gracefully. #B backup, PITR, and disaster recovery, DR.
All right, safety net time. Let's talk about backups and disaster recovery. For massive data sets, what are the primary methods for generating backups?
You generally have two main approaches. First is logical backups, typically using the MongoDump utility. This creates BSON dumps of your data. It's flexible, human-readable to some extent, and great for smaller clusters or maybe restoring just specific collections or documents.
But the downside for large clusters?
For large clusters, terabytes or petabytes, MongoDump is often just too slow. It has to read through all the data sequentially via the database engine. So the preferred method for large scale is physical backups. This usually involves using file system level snapshot capabilities. Think LVM snapshots on Linux, or cloud provider block storage snapshots like AWS snapshots, Azure Managed Disk snapshots, etc.
And these are much faster.
Extremely fast, often near instantaneous, because they capture the state of the underlying block storage device at a single point in time, without reading through the database layer.
But taking a raw file system snapshot of a running database sounds risky. Don't physical backups require specific consistency measures?
They absolutely do.
Yeah.
You cannot just snapshot the files of a running MongoDB process and expect a consistent recoverable backup. Writes might be in flight, partly written to disk. To guarantee a consistent snapshot across all the data files, you must ensure that no writes are happening during the snapshot window.
How do you achieve that?
Traditionally, this might have meant stopping the MongoDB process entirely, taking the snapshot, and restarting, obviously involving downtime. More practically, modern approaches involve either using file systems that support atomic snapshots, like CFS, or, more commonly with MongoDB, using features like synclock to pause writes temporarily during the snapshot, or using backup tools that coordinate with WireTiger's checkpointing mechanism, or using the oplog flag with MongoDump alongside the snapshot to capture the oplog state needed for recovery synchronization. Cloud provider backup solutions often integrate these steps.
The goal of any modern disaster recovery strategy is usually point-in-time recovery, PITR. How is this achieved in the MongoDB ecosystem?
PITR allows you to recover the database not just to the time of your last full backup, but potentially to any specific second between major backups. The mechanism typically combines the two methods we discussed. You start by restoring the most recent full physical snapshot that gives you a consistent baseline checkpoint from, say, midnight. Then you use the archived oplog data, which you need to be capturing continuously, to replay all the subsequent operations that occurred after that snapshot up until the specific timestamp you want to recover to. E.g., recover to 10.35.1 scene AM.
This reliance on the oplog for PITR brings us back to oplog retention policies, doesn't it?
It's a crucial operational link. Your oplog retention window. The amount of time the oplog stores operations before capping must exceed your backup interval. If you take daily physical snapshots every 24 hours, you absolutely need at least, say, 25 or 30 hours of oplog retention configured.
Why the buffer?
To ensure that even if a snapshot backup run is slightly delayed for some reason, you can always bridge the gap between the last successful snapshot and the desired recovery point using the continuous oplog replay. If your oplog window is shorter than your backup frequency, PITR breaks down.
And the ultimate complexity, I imagine, is restoring a fully sharded environment using PITR.
Oh, it's an orchestration nightmare, frankly. You cannot just restore one shard. You must ensure you have captured and can restore consistent snapshots of every single component of the cluster, taken at roughly the same logical time. That means snapshots of every shard's replica set and the config server replica set.
What happens if they aren't consistent?
If the snapshots are taken asynchronously without coordination, the recovered state might be internally fractured. For example, the config server metadata might know about a chunk on shard A, but the snapshot for shard A might be from slightly earlier, before that chunk was migrated there. Queries could fail, data could appear inconsistent. High-level DR planning for sharded clusters requires strict, coordinated snapshot tooling or using managed backup services that handle this coordination.
Finally, let's quickly define the key metrics for success in Docker RTO and RPO. How does MongoDB stack up?
Right. RPO is the recovery point objective, basically. How much data are you willing to potentially lose in a disaster? By using strong write concerns like W majority, your acknowledged writes are durable on multiple nodes, meaning your RPO is effectively near zero. RPO is 0 seconds for committed data.
And RTO?
RTO is the recovery time objective. How quickly can you restore service after the disaster hits? RTO is typically dominated by a few factors. First, failure detection time. How long until your monitoring realizes there's a problem, maybe 10, 30 seconds. Second, automatic failover time, if it's just a primary failure, often 10, 60 seconds for raft election. And third, the actual data recovery time, which could be minutes if it only involves replaying a short oplog segment, or potentially hours if it requires restoring terabytes from snapshots and replaying a large oplog during a more catastrophic event, like losing a whole data center.
MongoDB hasn't stood still. It's continually evolving, integrating solutions for modern needs like event streaming and specialized analytical workloads. Let's look at change streams first. MongoDB's engine for change data capture, or CDC, hashtag B, change streams, CDC, deep dive.
Right. Change streams provide a powerful real-time feed of data modifications happening within your MongoDB collections, replica sets, or even the entire database. They essentially work by exposing the operational mechanics of the database replication process directly to applications.
How do they derive the events?
They derive these real-time notifications directly from the underlying oplog we've discussed so much. Every state-changing operation, insert, update, delete, replace, even DDL like drop collection, generates a corresponding change event document. This event includes details like the operation type, the full document affected, or just the deltas, the namespace, and importantly, a resume token.
This functionality sounds critical for microservices architectures that rely on event-driven communication. But what happens if the consuming application crashes or restarts? How does the system handle faults?
Fault tolerance is built right into the change streams mechanism via those resumable tokens. Every single change event notification includes a unique, opaque token. This token essentially encodes the event's precise position within the op log stream.
So the consumer just saves the last token.
Exactly. The consuming application is responsible for persisting the resume token of the last successfully processed event. If the consumer crashes or restarts, it simply opens a new change stream cursor using the resume after option, passing in that last saved token. MongoDB then picks up the stream exactly where it left off, ensuring strict ordering and guaranteeing at least one's delivery semantics without missing any events.
Scaling change streams in massive sharded clusters must present a challenge, though, particularly managing stream aggregation across potentially hundreds of shards or chunks.
It used to be a challenge. Pre-MongoDB 5.1, you typically had to open separate change streams against each individual shard and then somehow merge or aggregate these streams in your application logic, which was complex and error-prone.
What changed in 5.1?
MongoDB 5.1 Plus introduced the capability to open a single change stream against the entire sharded cluster or specific databases collections within it. The Mongo's query router handles fanning out the request and merging the events from all relevant shards behind the scenes. For extremely high-volume environments, say, exceeding 10,000 changes per second cluster-wide, the system further distributes the workload internally, allowing potentially multiple consumers to read from the unified stream metadata concurrently, ensuring throughput can scale with the cluster size.
And the key integration pattern for using these streams in production-grade event processing is almost always Apache Kafka, right?
Almost universally, yes. The standard robust pattern is utilizing the official MongoDB Kafka connector. This connector is specifically designed to efficiently stream change events directly from MongoDB change streams into designated Kafka topics.
What does the connector handle?
It handles the BSON to Kafka Wragger translation, schema management potentially, and crucially, it manages the persistence and usage of those change stream resume tokens, typically storing them externally in Kafka itself or another persistent store. This ensures that Kafka, which provides its own powerful partitioning, fault tolerance, and ecosystem, can receive the data reliably even if the MongoDB primary fails over or the connector process itself is restarted. It provides that robust end-to-end CDC pipeline, hashtag time series collections and MongoDB modernization, 5.0 plus to 8.2.
MongoDB's modernization efforts have also heavily focused on specializing its storage engine for specific common workloads. Time series collections are a major example, heavily optimized for things like metrics, sensor data, IoT workloads.
Exactly. Time series collections, introduced in MongoDB 5.0, aim to significantly reduce the storage footprint and dramatically improve query performance for data where time is the primary dimension and you have many measurements arriving frequently for the same source or sensor.
What's the core mechanism behind the optimization?
The core mechanism is automatic bucketing. Instead of storing every single data point, say, every temperature reading from a sensor every second as an individual BSON document, which has overhead, the system automatically groups consecutive data points for the same source into larger optimized bucket documents behind the scenes.
How are these buckets defined?
You configure the collection specifying the time field, and optionally a meta field, which identifies the source, like sensor did. MongoDB then automatically creates these buckets based on a time period, e.g. hourly buckets, and the unique value of the meta field.
What's the practical result of this internal bucketing?
The results are pretty dramatic. First, incredible space savings. We often see 70% to 90% compression compared to storing individual documents, mainly because the metadata, like censored and indexing overhead, are stored once per bucket instead of once per data point. Second, it enables highly efficient clustered indexes based on time and the metadata field. This vastly speeds up the sequential range queries, give me all readings for sensor X between time A and time B, that are typical in time series analysis.
We mentioned online resharding earlier as a way to fix bad shard keys. This capability, introduced in 5.0 Plus, is truly transformative for the long-term evolution of large data sets, isn't it?
Oh, absolutely transformative. It solves one of the biggest historical pain points of sharding, being permanently locked into a suboptimal shard key choice made years ago. Online resharding allows you, the user, to execute the reshard collection command and effectively change the shard key for an existing live collection in the background while the cluster remains fully operational and serving reads and writes.
How does it work without downtime?
The system internally handles copying the data to conform to the new shard key definition, updates the cluster metadata, and manages the transition seamlessly. It provides a non-downtime path to fixing distribution issues or adapting to changing query patterns, which is a massive win for L6 L7 operational stability and agility.
And looking at analytical needs, we're seeing the MongoDB engine even adopting columnar storage capabilities, starting around version 7.0. Why is this necessary alongside the traditional document model?
The standard MongoDB document model is inherently row-wise storage, meaning all the fields of a single document are stored contiguously together on disk. This is great for transactional OLTP workloads, where you typically fetch or update entire documents.
But bad for analytics.
But for analytical OLAP workloads, where you might only need to scan two specific columns, say sales amount and timestamp, across billions of documents to calculate an aggregate, reading all the other columns in each document, like customer address, product description, etc., is incredibly inefficient in terms of I/O.
Yeah.
Columnar storage physically switches the internal representation for specific collections or indexes to be column-wise. Data for each field is stored together contiguously.
What's the benefit?
This drastically improves compression ratios for analytical data. Similar values compress well together, and makes read efficiency for aggregate queries orders of magnitude faster, because the system only needs to scan the blocks containing the specific columns required for the query, ignoring everything else.
Finally, in the modern era, MongoDB has fully embraced the AML landscape with integrated vector search capabilities.
Yes, vector search, significantly enhanced around 7.0 and later, is absolutely critical for modern AI-powered applications. It allows you to store, index, and efficiently query high-dimensional vector embeddings, the numerical representations of data, like text, images, audio, generated by machine learning models.
What does this enable?
This directly powers semantic search, allowing users to search based on meaning or concept, not just exact keywords. It also enables recommendation engines, find products similar to this one, image similarity matching, anomaly detection, and many other AML use cases, all integrated seamlessly within the operational database using new query operators like vector search alongside traditional filters. It brings vector similarity search close to the source data. ## security and compliance.
For enterprise adoption and operating in regulated industries, security isn't an add-on, it's a non-negotiable architectural layer. Let's start with the basics. Protecting data at rest.
Right. Encryption at rest is the absolute baseline expectation now. WiredTiger natively supports transparent data encryption, typically using strong standards like AES 256 for the entire data set on disk, including data files, index files, and the journal logs.
How are the keys managed? That's always critical.
Crucially, the encryption keys themselves are managed externally outside of MongoDB. The system integrates with standardized key management systems, KMS, via protocols like KMIP, Key Management Interoperability Protocol, or through specific integrations with cloud provider KMS services like AWS KMS, Azure Key Vault, Google Cloud KMS. This ensures a strict separation of duties between the database administrators and the security team managing the keys.
But perhaps the truly advanced capability, pushing security further, is keeping sensitive data encrypted even during query processing. Let's talk about client-side field-level encryption, CSFLE.
Yes. CSFLE, introduced around version 4.2 and significantly enhanced since, shifts the responsibility and the trust boundary entirely to the client application. Specific sensitive fields within a document, think PII, like social security numbers, credit card details, patient IDs, are encrypted by the MongoDB client driver before the data is ever sent over the network to the server.
So the database only ever sees ciphertext.
Exactly. The database server receives, stores, and indexes only the encrypted ciphertext for those designated fields. This maintains extremely strict compliance, as the sensitive plaintext data never leaves the trusted client environment. And MongoDB has implemented specialized, though limited, queryable encryption techniques that allow the system to perform certain types of queries, initially equality matches, with more capabilities being added, directly on those encrypted fields without ever needing to decrypt the data on the server side.
And for operational compliance, ensuring only authorized access and tracking activity, we rely on robust controls and logging, right?
Absolutely. Role-based access control, RBAC, is mandatory for any serious deployment. This allows defining granular permissions, read, write, create, index, etc., at the user or application level, scoped to specific databases or collections. This is often integrated directly with enterprise authentication systems like LDAP or Kerberos for centralized user management.
And for audits.
For compliance requirements like GDPR, ADPI, PCI DSS, etc., enabling MongoDB's auditing feature is essential. This allows you to configure the system to create comprehensive, potentially immutable logs of specific database events. This includes things like authentication successes and failures, user privilege changes, DDL operations, and optionally even all read-write data accesses, DML. These audit logs are critical for demonstrating compliance during audits and for forensic investigation after a potential security incident. Okay, we've really built up the theoretical and the mechanical foundation now. Let's transition into applying this knowledge. How does this play out in real-world, high-stakes L6, L7 engineering design or troubleshooting scenarios?
Right. If we connect this to the bigger picture, the true measure of an L6, L7 engineer isn't just knowing the theory, it's applying it effectively to preempt failure or solve complex problems. Let's start with a classic design scenario. Okay, here's the setup. You're designing the database for a new global e-commerce service. You're expecting terabytes of data eventually, millions of users globally, peaking at maybe 10,000 plus operations per second. The single most critical decision you need to make up front is the shard key strategy. What immediate red flags should we look for in potential keys, and what's the optimal path forward?
The immediate, flashing red light, siren's blaring red flag, is using any kind of strictly monotonic key. That means a simple sequential integer ID, a timestamp if inserts are always chronological, or even the default objective if your application inserts are happening in strict time order from a single source.
Why is that so bad here?
Because the workload is inherently append-heavy. New orders, new user signups, new product reviews, they all tend to happen now. With a monotonic key, all these new writes pile up on the single shard that holds the highest key range. This creates a massive imbalance, resulting in a singular hot shard that takes 100% of the write traffic, while your other expensive shards sit mostly idle. It completely negates the whole point and cost of sharding for write scaling.
Okay, so we need a key that provides high cardinality and ensures uniform write distribution. What are the generally recommended key types for this kind of e-commerce scenario?
For pure write throughput and maximizing distribution across a large number of shards, often a hash key is the simplest and most effective choice. For example, hashing the userid field, or maybe the orderid. Hashing pseudo-randomly distributes the writes across all available shards, effectively eliminating the hot shard problem for writes and maximizing write parallelism.
Are there downsides to hashing?
The main downside is that range queries on the hashed key become impossible. So if most of your critical queries involve targeted lookups or ranges based on user ID, or maybe geography, a compound key might be necessary. For example, something like userid1, order date. Maggots1 could work. You get good distribution based on userid, but queries for a specific user's recent orders are efficient. The key, pun intended, is to design the compound key carefully to minimize the number of shards that need to be accessed for your most common query patterns.
And what about managing global latency and potentially data residency compliance requirements for European or Asian customers?
That's where zone sharding becomes absolutely essential in a global deployment. You first define logical zones, perhaps US, US East, APAC South. Then you associate specific shards physically located in those regions with those zones.
And then you create rules.
Exactly. You then define sharding rules that mandate that data meeting certain criteria, like a document where user country, FRR, must only reside on shards that belong to the designated EU West zone. This physically aligns the data with the geographic region of the users, minimizing query latency and helping enforce data sovereignty regulations like GDPR.
Okay, let's say despite a good key, a shard still becomes temporarily hot due to an unexpected event, like a flash sale driving huge traffic to specific products or users. What's the immediate mitigation strategy before you consider something drastic like resharding?
Mitigation starts with rapid analysis and targeted action. If the hotness is primarily due to a read spike, everyone looking at the same sale items, the first tactical step is often to leverage read preference secondary. You can configure your application or drivers hitting that hot shard to direct the majority of their read traffic specifically onto the secondary nodes of that specific shard's replica set. This offloads the primary, freeing it up to handle writes.
And if it's a persistent problem or a write hotspot?
If the problem is persistent, or it's primarily a write hotspot, and analysis shows the shard key itself is fundamentally flawed for this workload pattern, then there's often no escaping it. You'll need to plan for using MongoDB 5.0 Plus's online resharding capability to transition that collection to a key that provides better long-term distribution for the observed traffic.
Okay, let's move from cluster design to internal transaction mechanics. We established that WiredTiger's MVCC uses optimistic concurrency control. Can you walk us through a scenario where two transactions might clash, focusing on how the right conflict detection mechanism actually works?
Sure. Remember, in an optimistic concurrency model, transactions don't take heavy locks up front. They proceed assuming they'll succeed, and only check for conflicts at the very end, during the commit phase.
Okay, set the scene.
Imagine transaction DLRO starts and reads document source. Internally, it gets a snapshot timestamp. Let's call it $2. Shortly after, maybe concurrently, transaction $T starts, reads the same document sellers, and gets its own snapshot timestamp, TF2. Now, $2 goes ahead and successfully updates document T2 and commits. Then, a moment later, 2F2 tries to update the same document dollars based on the version it read earlier and attempts to commit.
How is the conflict detected when 2 tries to commit?
The conflict is detected at the point $2 attempts to commit its write to $6. The system checks, has the document Cito that $2 is trying to write been modified by any other transaction, in this case $2, whose commit time occurred after $2 took its initial snapshot, $2.
Ah, so it checks if 2's view is stale.
Exactly. If this condition is met, meaning $2 committed a change to $6 after $2 started its work, but before $2 tried to commit, then $2's view of $6 is now provably stale relative to the globally committed state. The system declares a write conflict, and $2 transaction is aborted. It fails.
Okay, so has failed due to a write conflict. What is the standard expected application level resolution pattern for this?
Since MongoDB signals this failure with a specific write conflict error code, the application code must be written to anticipate and immediately catch that specific error. Upon catching it, the application cannot simply try to recommit the failed changes. That won't work. It must implement robust retry logic.
What does retry logic involve?
It means the application needs to roll back any local state changes associated with the failed transaction, reread the necessary data from the database, getting the latest committed version, including tying the one's changes, re-execute the business logic for the entire transaction from step 1, and then attempt the commit again. This retry loop is a hallmark of building highly available services on top of optimistic concurrency systems.
We discussed earlier the critical operational threat of a long-running transaction, holding on to an old snapshot, the hazard pointer, or history store bloat issue. Can you re-emphasize exactly why one single misbehaving transaction, holding a snapshot open for an extended period, say an hour, can severely degrade the entire cluster's performance?
It's because that one transaction acts like a dam, blocking the flow of garbage collection for historical data. If an application holds a snapshot open for hours, maybe it's a paused debugger session, maybe it's a badly designed batch job or ETL query that never closes its cursor, it essentially pins that old snapshot timestamp to apps.
And that stops cleanup.
Yes. It prevents the WireTiger garbage collector from cleaning up any older versions of any documents that were created before 2AS but were subsequently deleted or modified after 2AS. If the cluster's write volume is high during that hour, the history store, where these old versions live, quickly explodes in size, consuming potentially huge amounts of available RAM.
Leading to cache thrashing.
Precisely. This forces the database engine to spend excessive CPU cycles managing this bloated historical data, instead of focusing on the current working set. Active, frequently accessed data gets pushed out of the main cache to make room for history, leading to severe cache thrashing. Latency for every other concurrent operation skyrockets as the database constantly has to fetch needed data from slower disk instead of fast RAM. It's a cascading failure mode triggered by one slow client. All right, let's talk query performance. Query optimization at L6, L7 scale isn't about guesswork or just adding indexes randomly. It requires a systematic methodology, often starting with eliminating full collection scans, call scan. A foundational heuristic for designing effective indexes is the ESR rule.
Okay, define the ESR rule for us. What does it stand for, and how does it guide compound index design?
ESR stands for equality, sort, range. It's a powerful heuristic that dictates the optimal order of fields within a compound index to maximize its efficiency for a given query.
How does the order work?
The rule says, first, in your index definition, place all the fields that your query uses for exact matches. Equality filters like status, active, or userid 123. Second, place any fields that your query uses for sorting the sort fields like order date, Manica 1. Finally, at the end of the index definition, place any fields that your query uses for range-based filters. Range filters like price, 500, or timestamp, or my timestamp, ISO date.
Why this specific order? Equality, then sort, then range.
Ordering the fields this way allows the database query planner to use the index most effectively. The equality predicates rapidly narrow down the potential results set to a small slice of the index, The sort field then allows the database to retrieve those results in the already sorted order directly from the index, avoiding a costly in-memory sort operation. Finally, the range predicates can be efficiently applied to that already narrowed and sorted subset. Reversing the order makes the index much less useful.
The ultimate optimization goal, especially for very high-frequency queries, is often to achieve a covering index. Can you explain the criteria for an index to be covering, and also the associated cost or trade-off?
A covering index provides the fastest possible query execution because MongoDB can satisfy the entire query, both finding the matching documents and retrieving the requested fields purely by using the index metadata. It never has to perform the extra step of fetching the actual full documents from the underlying collection storage.
What are the strict criteria for an index to cover a query?
The criteria are strict. The index definition must contain all the fields required for the query's filter predicates, the find part, and all the fields required for the query's projection, the fields you're asking to be returned, the projection part. If the query needs even one field that's not in the index cannot cover it.
Okay, sounds great for read speed. What's the cost?
The cost is primarily significant write amplification and increased storage overhead. Since the covering index contains copies of many fields from the document, every single write operation, and insert, update, delete, that modifies any of those index fields must now update not only the collection data, but also this potentially much larger index structure. This increases the overall disk I/O, CPU usage, and latency for write operations, and also consumes more disk space. It's a classic read performance versus write performance trade-off.
So, putting it all together, if we diagnose a slow query in production, what's the systematic optimization strategy an L6, L7 engineer should follow?
It's a methodical process. First, diagnosis. Run the query through explain execution stats. Don't just look at explain. You need the execution stats. Analyze the output carefully. Look at the winning plan stage. If it's call scan, you definitely need an index. Look critically at in returned, number of documents matching, versus total keys examined and total docs examined. If the database examined millions of index keys or documents but only returned 10, your index is likely inefficient or maybe just missing entirely for that query pattern.
Okay, diagnosis complete. What's next?
Second, implementation. Based on the diagnosis and applying the ESR rule, design the optimal compound index. Then create the new index. Critically, in production, you should always create indexes in the background to avoid blocking application rights. Even better, consider creating and testing the index on a secondary node first to assess its impact on replication and resource usage before rolling it out to the primary.
In the final step.
Third, validation. After the index build completes, rerun the explain execution stats on the query. Confirm that the winning plan now shows an IX scan index scan using your new index. Verify that total keys examined is now much closer to end returned. Use the database profiler or application monitoring to confirm that the actual query latency has decreased significantly, and double-check that you haven't inadvertently introduced new bottlenecks in the right path due to the added index maintenance overhead. It's an iterative process of diagnose, implement, validate, #tagoutro.
Well, we have certainly completed an exhaustive journey today. We went from the abstract theoretical philosophy of CKP and ACID, dove deep into the internal mechanics of WiredTiger's MVCC and checkpoints, and explored the distributed consensus driven by Raft principles that underpins replication.
Yeah, it's a lot to cover. I think the essential knowledge for that L6, L7 mastery really boils down to recognizing that the system's true performance, ceiling, and reliability aren't just determined by raw hardware specs. They're fundamentally constrained by your architectural decisions,
Such as?
such as understanding the critical role of core mathematics in maintaining correctness during failures, the absolute necessity of monitoring MVCC snapshot holders and history store size to prevent operational thrashing, and maybe above all, the absolute priority of selecting the right shard key from day one to ensure long-term scaling viability. These aren't just details, they're foundational.
It really is a profound engineering concept when you think about it. The MongoDB document model appears deceptively simple and wonderfully flexible at the application layer.
That's its appeal.
But that flexibility is bought, it's enabled, by this immense, complex layer of underlying distributed systems engineering. We're talking Raft-inspired consensus, sophisticated MVCC versioning, distributed ACD implementations, checkpointing algorithms, all working constantly in concert just to maintain consistency and durability in an environment where network failures and node crashes are not exceptions, but constant, unavoidable factors of life.
Exactly. And the real challenge, therefore, for engineers operating at scale is not merely using the system's features. It's fully internalizing the inherent trade-offs and developing the intuition to anticipate when and how those internal guarantees those safety mechanisms might be tested or even break down under real-world production stress.
So, as a final provocative thought for you, our listener, to take away today, take a moment to look critically at your own most important application workflows that rely on MongoDB. Have you truly thought through and accepted the latency cost of using strong consistency? Majority reads writes, linearizable reads where it's needed? Or are you, perhaps unconsciously, gambling on the higher performance offered by weaker consistency, local reads, W.1 writes, hoping that failures won't happen at the wrong moment?
Understanding and consciously choosing where you sit on that fundamental operational balance, deciding what level of availability you are truly comfortable trading for what level of consistency and durability, that's the genuine hallmark of a seasoned distributed systems expert operating at the L6, L7 level.